Oh my, okay. Okay, everyone. So welcome to lecture 26. Wow, 26 lectures already. We are doing frequency hop spread spectrum, right? For ECE3311 Principles of Communication Systems. All right. So up until now, we kind of made this really nice transition throughout the course, and we're near the end. Remember, there are 29 lectures. At least that's what I indicated in the course syllabus. So there are 29 lectures that are in this lecture, in this course, and we kind of made this really nice, super cool transition all the way from sort of creation of the universe all the way until now. And how so? Well, let's graphically look at the timeline. Okay. So what have we looked at? Well, if we look at the course syllabus, right? So here's the beginning. Let me draw this nice, right? Beginning. Right? And what happened is we started, right, with baseband modulation schemes, right? We looked at how do we convert information into electromagnetic signals, right? So there was baseband. Okay, baseband signals, and we looked at both. First of all, like the continuous time. Let me put it another way. Analog. Baseband signals. Digital. Yeah. Then, okay, so here we looked at, first of all, everything here was single carrier, right? It was actually very specific. It was everything centered at 0 hertz, right? 0 hertz. Then we made the jump, okay? We made this very important jump, whoop. And very importantly, at that jump, we did this. Okay, and then we went to passband signals, first analog, like AM and FM and PM, okay, and DSBSC, right? And then we went digital. Okay, so passband signaling and digital. And the difference, digital, yeah. So here, okay, continuum of time. Here we're very specific. Things change every TS seconds. Everything is defined. Every amplitude, every phase, every frequency is defined every TS seconds. Same thing here. Every TS seconds, something's defined. We looked at in the case here things like Manchester coding. I know, somehow that's always on my mind. Manchester coding and polar and unipolar and all that jazz. Okay, and here, so we got like AM and FM and PM. What did we have with analog? Well, we looked at analog and we were looking more or less at like things like PAM, although that's also kind of a digital, and PCM. We looked at how these things were converted between the analog domain and the digital domain. So if we had an analog waveform, how do we digitize it into ones and zeros, and how do we return it as an analog signal? Correct? Right. And then, of course, we had DSB, SC, and we had SSB, and we had VSB. And then digital, we started playing around with things like ASK and PSK and QAM and FSK, right? And just as before, so these two were both, all of these, sorry, they were all single carrier. And that's just a way of conventionally saying the information is not manipulated. It's like, it's all stored. It's all like one big blob. Okay, we don't divide it across the frequency domain. We divide it temporally, right? And then we jumped from there, next slide, okay, into things like multi-carrier. Multi-carrier. And here we had the fun stuff of, like, we were looking, okay, still centered at FC, but we had like F1, F2, Fn, small narrowband, a narrowband carrier for each, whose total sum, right, the aggregate is a single waveform, a composite waveform, and that's what we send over the channel at FC. Okay, and one example that we saw of that is OFDM. Okay, and we only touched upon OFDM. We didn't go too much more deeper into that. Then we went into spread spectrum communications. So far, what we have done here, okay, I really want to emphasize this. What we started over the last week or so is we've started manipulating frequency and time, very specifically. And you can actually go more crazy, right? So we've been manipulating. Okay, that sounds kind of negative. Okay, harnessing. Yeah, that sounds much more like less negative. Okay, so harnessing the frequency and time domains. Okay, harnessing frequency, time domains. Alrighty, so we got that. And so we looked at direct sequence spread spectrum last week. Okay, and we looked at things like processing gain. Okay, in order to sort of distribute the information across frequency, okay, across time, the information's embedded in there, and the way you pull it out is through some very fancy mathematics that relate to correlation. Today is another type of spread spectrum. So this is multi-carrier. And this is spread spectrum. Let's deal with frequency hopping spread spectrum. So that's today's lecture. That's lecture 26. Okay. So recap from direct sequence spread spectrum. You had something called a pseudo, if I can spell it, pseudo-random noise. So we either refer to this as PN or PRN sequence, okay? And what happens is this repeating pattern, that looks like noise for individuals, communication systems, you name it. For everyone else, I'm going to put it not in the know. But for somebody with a matching PN sequence, with matching PN sequence, okay, because the way you divide, the way you create, okay, the way you create the PN sequence, all right. So it's just like shift register. There is a mathematical pattern. It's just, to anybody who doesn't know what that mathematical pattern is, or the setup, or the generation of that, looks like noise. But people who know what the pattern is, right, and they implement it at the receiver, totally know. Like, they totally know what that is, okay? And that allows you to extract out the signal, okay? totally known. And that's what we want, right? We saw, and this is sort of like a very, very kind of a fun drawing. So if this is time, this is your chip periods. Okay. Mu, 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 mu. This is your original signal. Let's say it looks like, should be multiples. So let's say it is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and whatever, right? And then let's suppose your PN sequence looks like this, or part of it. Okay, and remember, this is +1, this is -1. What happens when you multiply? Okay, so PN sequence CT and your transmitted your baseband signal, message signal M of T. What happens when you do? Okay, when you multiply this thing together, what do you get? Right, M of T multiplied. Remember, it's multiply, not convolve. With C of T, what do you get? What do you get? So what's 1 times 1? 1. Okay, cool. 1 times -1, -1. And so on. So we do this product. And what's -1 times -1? 1. And then 1 times -1, -1. Okay, -1 times -1, 1. And 1 times 1, 1. So this purple is our spreaded signal. And what happens if, let's say, we have the identical, once everything's aligned at the receiver, and remember, PN sequence is green, and we have the identical PN sequence, what happens if we multiply the PN sequence at the transmitter with the PN sequence at the receiver? What should the answer be? Well, it's either going to be -1 times -1 or 1 times 1, which means that it's all 1. We get the original M of T back, right? And what happens is these PN sequences are hundreds of chips long. If I don't get it exactly, if I multiply a PN sequence against a spreaded signal with a different PN sequence, I'm just going to scramble it more. I'm not going to extract it out. It'll still look like noise. Perfect. Because that's exactly what I want my spreaded signal to look like, is noise. Noise, when it's not spreaded yet, unspreaded, and when it is spreaded and it's the right PN sequence, I get the original signal out. And when I try and unspread the wrong spreaded signal, it still looks like noise. So at the end of the day, spectrally, if I had cross frequency, signal 1, spreaded signal 1, spreaded signal 2, and spreaded signal 3, okay? And they are centered at boop, FC. If I use the right PN sequence to extract out the blue, what should the frequency, what should it look like? It'll look like this for blue, because I despread. So it goes back, so let's say the LC is the processing gain. It'll be 1 over LC, the bandwidth, and all the power gets redistributed within that new bandwidth, or the original bandwidth, right? How about the other two signals? They remain to be spreaded. So it looks like that. And what's cool about that? Because look at the interference contribution of the signals. Like if you zoom in here, oh boy, look at that. I get 1 Lfsr, the amount of interference contribution from those other signals. Not bad. That's a price to pay, but it's not bad for my like decoding my transmit signal with everybody transmitting at the same time. All right. Now, let's zoom in. So right now, that's DSSS, right? Correct? So, and that uses the PN sequence, okay, to spread, despread signals, right? Now there's another type. Okay, we'll migrate over to the other type, the frequency hopping spread spectrum. So again, this PN sequence is important because it's pseudo-random. It's like my password, right? Well, kind of, sort of. What happens is, this is a key, right? The pseudo-random noise sequence. So pseudo-random means the key is being transmitted in plain sight. Well, sort of, but the thing is that the effects of that look completely random to anybody without that knowledge of what that key looks like. But if you have that knowledge, if you know how to generate that pseudo-random noise sequence, you can unlock and you can unspread the DSS sequence. Same thing can be with the frequency hopping spread spectrum. What happens here, the PN sequence is designed. What it does is the PN sequence determines the hopping pattern of the FHSS. What do you mean hopping pattern? Okay, so the way something like, for instance, Bluetooth works like that. So Bluetooth, right? What you use for like your headsets and stuff. There's both classic and there's also Bluetooth low energy. Bluetooth low energy, right? BLE. What they do, okay, is the following. You have n possible carriers. So, this sounds like OFDM to me. Sure, but it's different. What happens is, let's say you have FC1, FC2, FC3, FC4, FC5, FCN. What happens is I'm going to say TS seconds, okay? What will happen is the following. So the first TS seconds, information is transmitted to a receiver, a Bluetooth receiver, okay? And then what happens is the transmission changes carrier frequency. It goes here and stays on that for TS seconds and communicates more information. But what's really cool is that the transmitter and receiver are in sync with each other. So what happens is transmitter communicates to receiver, then they change the carrier frequency together, change to another carrier frequency together, change to another carrier frequency together, another one together, another one together, another one together, another one together, another. So what they do is they do this hopping. They do frequency hopping. And they do this dance in a way, okay, that to the outside observer, it looks random and it's difficult to track. But then how do you pull off something like the transmitter and receiver following each other? So what ends up happening is at the TX and at the RX, both of them have the same pseudo-random noise sequence. So the pseudo-random noise sequence in this case dictates the hopping pattern. So as long as they're clocks, right? As long as they're in sync with each other, they both are hopping together. They don't have to go back and forth saying, what's your pattern next? Da, 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 da. No, there's no other communication. They just know because they share the hopping pattern together. So they're always in sync, but to the outside world is like, what the heck? How do I track this? This is impossible. Where are you going next? And by the time you get to the frequency that you want to start, let's say, listening or decoding or getting information, they're already on to the next one. So it's beautiful. Oh, this thing is beautiful. So yeah, frequency hopping spread spectrum, very different, totally different. Okay. So let's go into the notes a little bit. Okay. Okay. All right. So okay. So one thing I did not talk much about, and I think it's a little bit important to talk about, is how do we generate the pseudo-random noise sequence? Okay. So that's the other thing is. There's an, okay, I'm going to go back to the whiteboard. This raised a very important point. So that's, okay, so first of all, the frequency hoppy spread spectrum concept, okay? But I want to go back. Let's say, let's focus. So the key thing here is that PN sequence. You notice it's in the place of honor, if you will, of both of these schemes, DSSS and FHSS, right? So it's kind of critical. So how do you generate this? So what are the properties? So generation. And the other critical thing is what makes a good PN sequence? PN sequence. So, so the main thing, okay, so let me answer the first one. The critical thing about what makes a good PN sequence, and the slides already said it, is that I want, let's say, okay, PNI, so the ith PN sequence, and PNJ, okay, assuming that they're not equal, to be uncorrelated. What does that mean? So that means that there is no similarity between the two, right? Like absolutely no similarity. And the reason for that is, imagine you have two transmissions, Bluetooth low energy transmissions going on, and then there's a string of chips, okay? That's happening at the same time of the two different PN sequences that actually match just by fluke. Because again, like let's say we just created these PN sequences, and then there are two PN sequences that are happening at the same time that happen, like, you know, just by fluke, that match, are identical, you know, for a bunch of chips. So like, for instance, like this. So let's say here's PNI, PNJ. And this segment and that segment at this time instant to this time instant, let's say T1 to T2, let's say they're a match. They're identical. What happens? What's going to happen is, in the frequency hopping spectrum case, they're going to be at exactly the same frequency. Remember, every Bluetooth link, that's the other thing, every Bluetooth link, as an example, shares the same frequency. It's not like I have FC1, FC2, FC3, FC4, FC5. It's not like this. We don't have, let's say, one Bluetooth device and another Bluetooth device. We don't have, let's say, this type of hopping sequence here. And another, so we don't have, let's say, this situation where this is, let's say, one link number one, and that's link number two. No, absolutely no way. This is what we have. We have them all in the same channel. They're just all kind of hopping around each other. And because they're uncorrelated, the possibility of them colliding is minimal, right? But if there's correlation, they'll both be aligned on exactly the same frequencies for who knows how long, and they'll both be interfering with each other. The reason why Bluetooth works, right? Part of the reason why Bluetooth works and frequency hopping spread spectrum works is the fact that because of the uncorrelatedness of the PN sequences, because it's random, we're really counting on the fact that the communications will not collide with each other in the frequency domain, right? But if there is correlation like this, right, there will be a segment where who knows how many hops, they'll be colliding, and all that data gets corrupted, okay? All right. So what's really important is how do you design a PN sequence, right? So how do you design it? So here, right, there's a couple of ways. There's something called the M sequence, and then there's also called gold codes, right? And each have their own advantages and disadvantages. But let's look at M sequences. I'm going to pull up. Let me get a good. That's weird. I thought I had a good example here. Silly me. Here we go. So here, this is from class test 7 from B term 2018. So the question asks, okay, so this is a good example. So this is for an M sequence. Okay, so the question, this is from B term 2018. So the question is, you have an M sequence, PN generator. And the way we implement these things is something through a linear feedback shift register. I mentioned this last week, but now we're going to go into the details of this. Okay, so we call otherwise known as an Lfsr, right? So what happens is this implementation has the following. Okay, so what ends up happening is usually we use this guy, right? This is an XOR. Exclusive OR. So what will happen is we either have like delay elements, okay? Okay, and sometimes, and what the feedback part is, so notice this goes from left to right. What we can do is the following. So let's say we take this guy and this guy, we XOR them. Okay, and then feed it back. So what ends up happening is we have an initial state here, 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 here. We could zero it out, or we can put a 1. We can initialize it any which way. And what will happen is it'll just create this train of binary outputs that ultimately form our PN sequence here. All right. So the question asked in this case, you have 3 delay elements. Okay, so 3 times this. Okay. Moo. So 3 delay elements. So let's draw it out. Delay 1, delay 2, delay 3. Okay. We're the leftmost delay element. The input is xi. The output, okay, is xi minus 1. Okay, that's the previous one, right? This obviously is going to be xi minus 2. This is going to be xi minus 3. Okay? And then they say, draw the feedback path, this guy, all right, is going to be the combination. So they say xi is actually xi minus 2 XOR with xi minus 3. So what's that? Actually, I just drew it before. So silly me. So you take that, XOR them, boop. That's what you got, right? So, and then what you do is now you got that. So that was A. Draw this thing. Okay. Now, second is you have this table. Okay. I was really nice. I gave a table. So the table is you have x all right. So table xi minus 1, xi minus 2, xi minus 3, xi. Okay. And I said initial condition 0, 1, all ones. Boop, boop. Okay. So what you need to do is propagate this thing through. Okay. So what you need to do is the question is propagated through, and then it says at what point do you see this pattern, this thing repeating? So when does that happen? Okay. So you chug through this. So you say, okay. So let's say we initialize, we go back to this diagram. Okay. The initial condition is what? So that was 0, 1, 1, 1. Okay, cool beans. So advance 1 clock cycle. Okay, shift register. So delay. Okay, so this no longer happens, right? That gets pushed here. Okay, that value propagates through the delay element, 1 clock cycle. That element goes there. This element gets propagated to the other side of the delay. Okay, and that cancels there. And remember that there's no delay with the XOR operator, right? No delay. So don't say, oh, it's got a loiter there. Blah, 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 blah. No, there's no delay. It instantaneously processes. Okay. So what happens? Well, before the clock cycle, right? It had these elements, right? So it had 1 and 1. So what's XOR? Zippo. So boop, boop, boop. Correct? Yep. So what we got is 0, 1, 1, 0. So let's put it there. 0, 1, 1, 0. Right? Okay. Next. So remember, so now, what's the value here? Well, after that clock cycle and I push through the delay, the XOR instantaneously processes what the next value should be here, right? What is that? Still 1, 1, right? So it should be still 0, okay? Then the clock cycle happens, and everything propagates through, so it's another delay. So the 0 value goes, so 0, okay? That 0 value propagates over, so 0. That 1 value propagates over, so it's 1, right? And we hold off for now because the next clock cycle, what we care about is like when we instantaneously evaluate these guys. But so what we have here is 0, 0, 0, and then xi is still 0, right? So we go here, 0, 0, 1, and 0. Now, this is the interesting part. Let's execute this stage. So what happens? So 0, 1, now it's a 1, right? We had a value here, 0, that propagated through. So it's still a 0. That propagated through. So that's a 0. And the 0 here propagated through, that's a 0. Okay, good. So it's 0. Oh, wait. No, I take it back, folks. Sorry. See that there's no delay on the XOR. So shucks. See, silly me. So so it's 1 instantaneously. Yep. 1, 0, 0. Okay, 0. And then what happens is these guys 0, 0 produces a 0, right? So what happens when we're done with the clock cycle, it makes that. So what we get is 1, okay, that propagates through at the next clock cycle. That propagates through 0, 0, 0. So we keep on doing this, right? Every iteration. And eventually, what we're going to get back, when does it repeat? So this is 0, 1, 2, 3, 4, 5, 6, 7. So 4, 5, 6, 7, it repeats. So well, in this case, it's a very simple PN sequence generator. Just constantly creates this bit stream over and over and over and over and over and over. And that is what's used to either spread a DSSS signal or dictates the frequency hopping pattern. Now, the problem with the M sequence is it does suffer from correlation issues. So it's not really that great, but gold sequences is actually pretty good. That totally handles correlation a lot better. All right. All right. Okay. So that is how we generate. So again, the key thing here is at what point do you sample, right? What's the value of xi minus 1, minus 2, minus 3, minus 4, however long your shift register sequence is. Okay. All right. And this is sort of the mathematics on how to calculate exactly what we did. And the autocorrelation, right? So the autocorrelation, that just like this actually will come up later in a course, like let's say like 4305, when you're trying to do frame synchronization and you embed a sequence, okay? You embed like a Barker sequence in order to correlate to find out where the beginning of your frame starts. You do exactly something like that here, right? So this is how correlation works. The way correlation would work is you would take your sequence. Let's say this is your M sequence, and you would take your sequence again. Let's say the length is of M, and what you do is, okay, this is how you do it. So this is 1s and 0s, correct? What you would do is you would take these guys. Let's just double check. So what do we have here? Is literally the M. No, we want L. So okay, L. Sorry people. So what we want to do is we want to take the sequences and we want to shift them relative to one another by an amount M, right? And M is what changes. Sorry about that. So what you do is the following. You take, yeah, it's not M. Let me be consistent in my notation. So L. And these are identical. These are totally identical. And what you do is, okay, so let's say there's no difference. So M equals 0. So M is the sort of relative difference shift, if you will, is the amount of shifting between one and the other, okay? So what you got is, let's say shift is 0. They're identically matched. And what should happen if I multiply the two together? They should be, you multiply them together, element by element, and then you sum them. Okay? And if they're both like, I think they're ones and minus ones. Let me double check. No, they're binary. Okay. So in that case, what should you get? So if they should be, please. What they should be is 1 with 1 is 1, 0 with 0 is 0, and 0 and 1 should be 0. And then you sum them. So when m is equal to 0, this should be the maximum because it's identical. So it should be 1. Sorry, not 1, L, because you're summing them all together. But let's say I shift them by 1. What does that look like? It looks exactly like this. So it's offset by 1. And then you do the multiplication with each other. Okay? And what happens is you would take this guy and you would move him here. Okay? So you're still multiplying an L long, an L long sequence with an L long sequence. And what we want, ideally, is we really want this to be equal to 0. But we'll probably not get that. But we for absolutely, in order for this to be uncorrelated, we want this value of the correlation, right? So it's element by element multiplication, and then we add all of the results together. We really want this to be way less than L. So what ultimately, if we shift one sequence against each other and multiply them and sum up the result, what we really should have is something that looks like this. So L, that's when the shift is 0. That's when we're like lining up both of them. That should be the maximum because they are identical, right? But we really want something to look like that. This is the autocorrelation. Okay. And the reason for the autocorrelation, right, is that if I have any shifted version of that PN sequence multiplied by itself, it should not correlate at all. If it correlates even slightly, that's a problem, because then we might accidentally decode a message, but it's not at the right place, even though it has some non-negligible amount of correlation. And this creates errors and no one's happy. So we need to make sure that the PN sequence we generate is uncorrelated for its autocorrelation. So that's important. That's super important. Next is, okay, so here's some sample ones, right? And stages and where you can connect them up. But the other problem is when we have two completely different PN sequences. We want those two things for all m to be close to 0. We want that none of them to be correlated to any extent. And the problem is that M sequences don't really do a good job with that, but gold sequences do. Okay, so the way gold sequences work is actually rather complicated. You take two simultaneous M sequences and you kind of like have the two combined together in this kind of weird parallel implementation with a bunch of XORs all over the place, and that makes them more uncorrelated. Okay, so okay, and I think I already like. So let me. The way this would work, okay, with frequency hopping, I think I already described it heuristically, but the way frequency hopping would work in terms of an actual implementation is that you actually use an FSK modulator, okay? So this is all frequency hopping information, okay? And then the mixer, the way this would, okay, so let me draw it instead of like just talking about it. The way is that you would have data, you would have an FSK mod, and this here specifies the subcarrier. No, sorry, not the carrier, but the carrier frequency of the frequency hop. And that is determined by the PN sequence. And then it goes, you know, to channel. So this is at transmitter. And then at receiver, what the heck happens? Well, from channel, okay, you just undo it, right? You take, like, so you could do one of several things. So if we go back to here, what happens is you do the demixing, and then you do the FSK demod, right? And there's, of course, I'm leaving out some steps like you need to bandpass filter. So let's say here, again, so let's say use the PN sequence I. I'm overusing I. So let's get rid of that. Yes, cool beans. So what happens is, no, that should be I. But you're using some sort of PN sequence, right? And then use the same one here. Okay, use the exact same PN sequence. You might have to remember when we do the demod here, right, the mixing, we're going to have to filter out the higher frequency. We want to keep only one image, right? So we bring one down to baseband or wherever it is, and we reject its image, right? So there's going to have to be some sort of low pass filter. And then you do the FSK demod, right? So perfect. So and it's very serious. Like what happens is just like what we saw with super heterodyne receivers, right? With we want to pick out one frequency from an array of signals on different carrier frequencies. This is actually quite critical because if we don't select the right carrier frequency to demod down, we get garbage, we get noise, but we don't get the desired signal that's being transmitted at the transmitter, right? So, and then we have the sync. So for example, if let's say my data is at FC1, right? And that's what the mixer brought it up to, my receiver better be locked on to FC1, which if I demod that down to baseband, what's going to happen? So FC1, I'm going to have a signal at 0, and I'm going to have another signal at 2 FC1. So I want to reject that. But potentially what happens is, remember, I'm going to have other signals communicating, maybe nothing or maybe a ton. But imagine if I use the wrong FCI. I use this one at the receiver, assuming that my low pass filter is narrow enough and it only takes the desired, like, you know, that frequency hop, it will reject everything else. And if I demod at the wrong place, it's going to be either nothing or it's going to be someone else's signal, which is not what I want to decode, and I can't decode it because it'll be encrypted and all that. All right. So let's go here. So that's what happens. And I already showed that. Okay. And then what happens is there are some works out there with respect to the tracking of the. This is actually super challenging. So what basically, and this is sort of a parting note for this lecture, is you note, like, we already looked at synchronization, like, you know, sort of carrier offset, and we also looked at phase offset, and also the symbol period duration, and how we have to extract all that information, and transmitter and receiver have to be on the same carrier, same phase alignment, and same timing and such. So you can imagine now we're using chips that are a fraction of the time duration as symbol periods. This is now even more challenging. And so what ends up happening is there's actually a paper written by Pickholtz and several other folks in 1992. It was published. What ends up happening is what's critical is being able to establish, being able to time, to get exactly the right instant on the chip level where you need to, because imagine if you don't have, recall what happened with the autocorrelation. If the same M sequence is not perfectly aligned, right, between transmitter and receiver, we got problems. We cannot successfully decode, we cannot successfully despread or recover the correct carrier because, like, you know, FC1, FC2, FC3, because the autocorrelation theoretically should be close to 0. So Pickholtz came up with an algorithm that allowed us to be able to be in time sync between transmitter and receiver in order to successfully decode specially spreaded signals. All right, so this lecture really concludes our chat about direct sequence spread spectrum. And definitely, you know, the course textbook goes into a lot more detail about Pickholtz's approach. But really the walkaways here are PN sequence generation, in particular the M sequence approach. There is, of course, the gold sequence. You should check that out in the course textbook. It's a little bit more complicated. But definitely the understanding of how the PN sequence is generated as a line of shift registers from which the gold sequences are also created. And in particular, how it's used in order to create direct sequence spread spectrum signals, as well as frequency hopping spread spectrum signals. All right, so that concludes lecture 26 of ECE 3311.